Integration by partial fractions. Let p of x over q of x be a rational function where p of x and q of x are polynomials and q of x is non-zero. And the degree of the numerator is less than the degree of the denominator. If q of x can be factored into linear factors with no repeating factors, or another case where all the linear factors each have multiplicity of 1. So for example, the integral of x over x squared plus x minus 2 dx. If I factor, I get x over x plus 2 quantity x minus 1. I'm going to set up partial fractions to determine the two fractions where this came from. So a over x plus 2 plus b divided by x minus 1 is equal to x divided by x plus 2, x minus 1. My goal is to solve for a and b. I'm going to multiply both sides of this equation by the LCD, which is x plus 2, x minus 1. Then I multiply the right side by x plus 2, x minus 1. So I'm left with a times x minus 1 plus b times x plus 2 is equal to x. If I distribute the a and distribute the b and combine all the terms with an x and then combine all the terms without an x, I get a plus b times x plus negative a plus 2b is equal to x. So now we can set up a system of equations. If I equate coefficients, the coefficient of x on the left side equals the coefficient of x on the right side. So if I set the x coefficients equal to each other, I have a plus b is equal to 1. If I set up all the constants, I have negative a plus 2b is equal to 0. So here's that system of equations. I can solve by substitution, elimination, or put them in a matrix and use reduced row echelon form. If I solve that system of equations, a is equal to 2/3 and b is equal to 1/3. Instead of solving a system of equations, the shortcut is to choose x to be some numbers and figure out what happens. You can use a combination of both. You can use one method or the other. I usually use a combination of both. If I let x equal 1, I'm going to plug in 1 for x into this line here. I think it's the easiest. If x is 1, I have a times 0 plus b times 3 is equal to 1. So 3b is 1, which means b is 1/3. If I choose x to be negative 2, and I chose negative 2 to make this term a 0. So if x is negative 2, I end up with negative 3a plus b times 0 is equal to negative 2. So negative 3a is negative 2, so a is equal to 2/3. So either technique works. So I found my coefficients, a and b. I'm going to plug those back into this form, since this can be written as the sum of these two fractions, or known as partial fraction decomposition. So the integral becomes a over x plus 2. So 2/3 divided by x plus 2 plus b over x minus 1. So plus 1/3 divided by x minus 1 dx. So 2/3 times the integral of 1 over x plus 2 dx plus 1/3 times the integral of 1 over x minus 1 dx. So this is 2/3 times natural log absolute value of x plus 2 plus 1/3 natural log of x minus 1 plus c. You can leave your answer like this. You could bring these coefficients back up as exponents and condense the logarithm, which will give you natural log of x plus 2 quantity to the 2/3 times absolute value of x minus 1 to the 1/3. That whole quantity inside the natural log plus c. Case 2. The denominator q of x can be factored into repeating linear factors. The integral of 6x plus 7 divided by x squared plus 4x plus 4 dx. So I can factor the bottom. 6x plus 7 divided by x plus 2 quantity squared dx. So the partial fraction decomposition is a over x plus 2 plus b over x plus 2 squared equals 6x plus 7 divided by x plus 2 quantity squared. So for repeating linear factors, the numerator is always 1 degree less than the denominator. But you have to account for every time that that factor repeats. So this factor has multiplicity 2. To solve for a and b, I'm going to multiply both sides by the LCD, which is x plus 2 squared. So I have a times quantity, x plus 2 plus b equals 6x plus 7. So I'm going to choose x to be negative 2. If x is negative 2, the first term is going to become a times 0, which is 0. So I just get b equals 6 times negative 2 is negative 12 plus 7 or negative 5. So b is negative 5. If I choose x to be 0, you can pick any number you want. I think 0 is easy. I have 2a plus b equals 6 times 0 plus 7, or just 7. But I found b in the previous line. So 2a minus 5 is equal to 7. So 2a is 12. So a is 6. So the integral will turn into a over x plus 2. So 6 over x plus 2 plus b over x plus 2 squared. So plus a negative 5 divided by x plus 2 squared dx. And this is equal to this integral here. Since I did partial fraction decomposition on that rational fraction. So if I factor out a 6, 6 times the integral of dx over x plus 2 minus 5 times the integral of 1 over x plus 2 squared dx. The first integral is a natural log. The second integral is u substitution. If I let u equal x plus 2, du is exactly dx. So 6 times the integral of dx over x plus 2 minus 5 times the integral 1 over u squared du, which turns into u to the negative 2 du. So this is 6 natural log absolute value of x plus 2 minus 5 power rule u to the negative 1 over negative 1 plus c. So 6 natural log absolute value of x plus 2 plus 5 over u, and instead of a u gets replaced with x plus 2 plus c. Case 3. Q of x has non-repeating quadratic factors. The integral of negative 2x plus 4 divided by quantity x squared plus 1 times x minus 1 quantity squared dx. So the partial fraction decomposition, I'll do the linear factors first. So a over x minus 1, since it's a double root or has multiplicity 2, I'm going to have b over x minus 1 squared. For the x squared plus 1, that's an irreducible quadratic, which means it does not factor. So the numerator is going to be cx plus d divided by x squared plus 1. Again, the numerator has to be 1 degree less than the denominator, and then you keep descending until you get to the constant term. This is equal to negative 2x plus 4 divided by x squared plus 1 times x squared, x minus 1 quantity squared. If I multiply both sides by the LCD is x squared plus 1 times x minus 1 quantity squared. Then I'm left with a x minus 1 x squared plus 1 plus b times x squared plus 1 plus cx plus d times the quantity x minus 1 squared equals negative 2x plus 4. Okay, if I FOIL these two terms, and distribute it with this cx plus d, and I'll put the result in descending order. So a times the quantity x cubed minus x squared plus x minus 1 plus b times x squared plus 1 plus c times x cubed minus 2x squared plus x plus d times x squared minus 2x plus 1 equals negative 2x plus 4. Okay, if I let x equal 1, you can plug it into this line. I think this one is easier, since this will zero out and this will zero out also. So if x is 1, I have 2b. If I plug in 1 on the right side, I get 2, which means b is equal to 1. If I plug in 0 for x, I get negative a plus b plus d is equal to 4. In addition, I'm going to look at the coefficients of the x cubed term, which is a plus c is equal to 0. If I look at the coefficients of the x squared terms, negative a plus b minus 2c plus d, and there are no x squared terms on the right side. If I look at the coefficients of x's, a plus c minus 2d is equal to 0. Negative a plus b plus d is equal to 4, and I have negative a plus b plus d is the same thing. So I'm going to plug in a 4 minus 2c is 0. So negative 2c is negative 4. So I found c to be 2. Then I can plug in c for 2 or 2 for c into that c. So a minus 2 is 0. So a is 2. I have a B, and C, and I need D. And I have this last equation for x's. So A is 2, plus C is also 2. C is positive 2, which means this is a plus, so A is negative 2. So negative 2 plus 2 minus 2D is 0. There's a mistake. The equation for this x, there are negative 2 x's on the right side. So instead of this 0, this should be negative 2. Which would change this 0 to negative 2. So I have negative 2D is negative 2. So D is equal to 1. So if I plug in A, B, C, and D into the fractions, negative 2 times the integral of dx divided by x minus 1 plus the integral of 1 over x minus 1 quantity squared dx plus cx plus d, or 2x plus 1, divided by x squared plus 1 dx. So this integral is negative 2 natural log absolute value of x minus 1. The next one is a u substitution, and then power rule or inverse power rule, so 1 over x minus 1. The integral for the right term, I'm going to split it up into two fractions. So the integral of 2x divided by x squared plus 1 dx plus the integral of 1 over x squared plus 1 dx. This integral is a u substitution. U is x squared plus 1, so du is 2x dx. So the integral turns into du over u. So negative 2 natural log absolute value of x minus 1 minus 1 over x minus 1 plus the natural log of absolute value of u, which is the natural log of quantity x squared plus 1. I'll remove absolute values since that value is always positive. The last integral on the right is arctangent of x. So arctangent of x, there's no more integral sign, so plus some constant of integration. Case 4. Denominator q of x has repeating quadratic factors. the integral of 1 over x times the quantity x squared plus 1 quantity squared dx. So the partial fraction decomposition would be a over x plus bx plus c divided by x squared plus 1 plus cx plus d divided by x squared plus 1 quantity squared equals 1 over x times x squared plus 1 quantity squared. So if I multiply both sides by the LCD to get rid of all the fractions, I multiply both sides by x squared plus 1 quantity squared. So I'm left with a x squared plus 1 squared plus bx plus c times x squared plus 1 plus, there's a typo up here. Since I have bx plus c here, I can't repeat these numbers or these letters. So a, b, c, this should be a d, and this should be an e. So dx plus e. So plus dx plus e times an x is equal to 1. If I FOIL x squared plus 1 squared, I have x to the 4th plus 2x squared plus 1 plus, if I look at all the terms with a b, it's an x to the 4th plus x squared plus, if I look at all the terms with the c, it's x cubed plus x plus dx squared plus ex is equal to 1. So now if I equate coefficients, all of the x to the 4ths on the left side are a plus b. There are no x to the 4ths on the right side, which means it's equal to 0. If I look at the coefficients of x cubes on the left side are c. There are no x cubes on the right side, so that's equal to 0. For x squareds, 2a plus b plus d. There are no x squareds on the right side, so it's equal to 0. If I look at the coefficient of x's, c plus e, no x's on the right side. And then last equation, if I look at the constants on the left side are just a. The constant on the right side is a 1. So if I have c is equal to 0, I'm going to plug this 0 in for c here, which means I can solve for e. That means e is equal to 0 also. If I have a as 1, I'll plug it into the equation with the x to the 4th. So b is negative 1. If I have a, if I have b, I can plug it into this equation and solve for d. So 2 times a, or 2 times 1 is 2, minus 1 plus d is equal to 0. So 1 plus d is 0, which means d is negative 1. So that integral will turn into a over x. So 1 over x plus bx plus c over x squared plus 1. So plus the integral of negative x plus 0 divided by x squared plus 1 plus dx plus e. So plus the integral of negative x plus 0 divided by x squared plus 1 quantity squared dx. So the integral of 1 over x dx minus the integral of x divided by x squared plus 1 dx minus the integral of x divided by x squared plus 1 quantity squared. First one is a natural log. The next integral and the last integral are both u substitutions. So if u is x squared plus 1 du is 2x dx. So x dx is 1/2 du. So this turns into natural log absolute value of x minus 1/2 times the integral of du over u minus 1/2 times the integral of du over u squared. So natural log absolute value of x minus 1/2. This will be natural log absolute value of u, and then u is x squared plus 1. I'll drop the absolute values since x squared plus 1 is always positive. The last integral is power rule. U to the negative 2 du, add 1 to the power, divide by the new power. So I get plus 1/2 times 1 over u. So times 1 over u is x squared plus 1. No more integrals left, so plus c. Natural log absolute value of x minus 1/2 natural log of the quantity x squared plus 1 plus 1 over 2 times x squared plus 1 plus c. Integral of x squared minus x divided by x squared plus x plus 1 dx. Because degrees are the same, I have to divide, and you have to do long division for this one. Once you do long division, you get 1 minus 2x plus 1 divided by x squared plus x plus 1. I'm going to factor into x plus 1 quantity squared dx. The denominator does not factor, so I'll leave it as x squared plus x plus 1. Okay, I can integrate 1 with respect to x. So the integral of 1 with respect to x minus the integral of 2x plus 1 divided by x squared plus x plus 1 dx. This integral is a u substitution, where u is the denominator, x squared plus x plus 1. So du is 2x plus 1 dx. So this integral of 1 with respect to x is x minus the integral of du over u, which is x minus natural log absolute value of u plus c, which is x minus natural log absolute value of x squared plus x plus 1 plus c. The integral of cosine of x divided by sine squared x plus sine x dx. On this, I'm going to do a u substitution first. U equals sine of x, so du is cosine x dx. So the integral turns into du divided by u squared plus u. The denominator will factor. If I factor out a u plus 1, now I can do partial fractions. A over u plus b over u plus 1 equals 1 over u plus 1. If I multiply both sides by the LCD, a times u plus 1 plus b times u is equal to 1. If u is negative 1, I have negative b is equal to 1, so b is negative 1. If u is equal to 0, I have a is equal to 1. So that integral will turn into a over u, so 1 over u plus b over u plus 1, so minus 1 over u plus 1 du, which is natural log absolute value of u minus natural log absolute value of u plus 1 plus c. For this one, I'll combine these as a single natural log. So natural log of u over u plus 1 plus c. And then u is sine of x. So natural log absolute value of sine of x divided by sine of x plus 1 plus c. So sometimes a substitution is required before some sort of partial fraction decomposition. But if the degree of the numerator is bigger than the top, then you are forced to long divide. The integral of 1 over 1 plus e to the x dx. If I let u equal the denominator, 1 plus e to the x, then du is e to the x dx. I don't have an e to the x multiplied by a dx, so I'm going to divide by e to the x. So du over e to the x is equal to dx. When I replace this, I'm mixing u's and x's. So if I want to get rid of this e to the x in terms of u, I'm going to solve this equation in terms of u. So from here, u minus 1 is equal to e to the x. So du divided by u minus 1 is equal to dx. So the integral will turn into 1 over 1 plus e to the x is u times dx, which is du over u minus 1. So now I can set up the partial fraction decomposition. 1 over u times u minus 1 du. Both factors are linear, so a over u plus b over u minus 1 equals 1 over u times u minus 1. If I multiply both sides by the LCD, a times u minus 1 plus b times u is equal to 1. If I let u equal 1, and if I let u equal 0. If u is 1, I have b is equal to 1. If u is 0, I have negative a is equal to 1. So a is negative 1. Or you can equate coefficients. So this integral will turn into negative 1 over u, a over u, plus 1 over u minus 1 du, which is negative natural log absolute value of u plus natural log absolute value of u minus 1 plus c. So natural log of u minus 1 minus natural log of u. If I reverse the order, natural log absolute value of u minus 1 minus natural log absolute value of u plus c. I'll combine this as a single fraction. Or you can leave it like this. Just go back to x's at the end. U is 1 plus e to the x. So natural log absolute value of 1 plus e to the x minus 1 minus natural log absolute value of 1 plus e to the x plus c. The 1's cancel, so I have natural log of e to the x minus natural log 1 plus e to the x is always positive. So I can drop the absolute values. Natural log of e to the x is x. So x minus natural log of the quantity 1 plus e to the x plus c.